Hello, my name is Siavash Zangeneh. I'm presenting our work with Stephen Pruett and Professor Yale Patt on branch prediction with multi-layered neural networks. So far, traditional branch predictors have a huge problem. They cannot isolate correlated branches in the history. As a result, they cannot filter or ignore uncorrelated branches, and they cannot learn complicated functions. But recent work has shown that convolutional neural networks can actually discover these complicated correlations and use them to improve the prediction accuracy. But the conventional wisdom has been that you cannot use multi-layer neural networks for branch prediction. The main problem with that has been the cost of the hardware needed for training and the long warm-up time. But Tarsa and others have shown that you can actually train a CNN at compile time, and it works very well. All you need to do is you profile your target programs with enough input sets to generate a diverse training set. And then your training will generalize to other unseen inputs. With that methodology, the on-chip predictor only needs a CNN inference engine that doesn't need further training at runtime. Still, at runtime, branch predictors have strict latency and storage constraints. We're talking about a latency of only a few cycles here, which is much less than what typical CNN inference engines give you. Tarsa and others have done some optimizations to that end. And they could significantly reduce the inference latency of their CNN branch predictor. However, their storage cost is still not good enough. 148 kilobytes extra storage on top of a 64 kilobyte Tejas CL, only for a 4% MPK reduction, is not a really good trade-off. But we do not think that this high storage overhead is a fundamental problem with the CNNs. We think that by understanding the problem better and by using specialized components in conjunction with the CNNs, we can bridge the gap and increase the effectiveness of CNNs. And we're gonna use an example to explain what you mean. For our example, we're gonna use qsort as our case study. So let's first try to understand the overall algorithm. Qsort starts by partitioning its input into two halves. It uses a pivot, and it compares each element in the array to the pivot. It inserts the elements less than the pivot to the left partition and inserts the elements greater than the pivot to the right partition. After the partitioning is over, it's gonna check the size of the partitions. And if further recursion is necessary, it's gonna call qsort on each corresponding partition. For this example, we're gonna focus on one of these branches that guards the recursion. In particular, that branch that we wanna look at is highlighted in yellow. It's gonna examine the left partition and controls whether we wanna recursively call qsort on the left partition. Now, there's a simple way to predict this branch. What we need to do is to infer the size of the left partition from the global branch history. And we could do that by identifying the instances of that branch that I circled in red. Every time this branch falls through, we insert one item into the left partition. So we can simply count these instances in the global branch history to determine the size of the left partition. However, state-of-the-art predictors cannot do that. And there are mainly two reasons. The first reason is that there are uncorrelated branches that pollute the global branch history. The second reason is that we should only consider the current recursive instance of qsort. This is a non-trivial task for state-of-the-art branch predictors. But if we had a custom branch predictor that we designed just to predict this branch, we could achieve 100% accuracy. and we don't need that much state to do it. We just need a 2-bit saturating counter to keep track of the size of the left partition. Every time we start the partitioning phase, we reset the counter to 0, and every time we insert an element into the left partition, we increment it by 1. Then at prediction time, it's just a matter of comparing that counter to 2. Now, even though this works fine for this branch, it's not the general algorithm, so it's not useful in practice. But we're going to use this as a reference point to identify the inefficiencies of the CNN. So let's first look at the numbers. As you can see, CNN predicts the same case study branch with 99.3% accuracy. That's actually very good, especially compared to Tage, which predicts this branch with 94.7% accuracy. But the main problem here is the cost. The CNN needs more than 5 kilobytes of storage for the prediction, while our custom predictor only needed 198 bits of storage. This difference is very significant. And this difference is the result of the more general nature of the CNN. It's the fact that we have these fully connected neurons that can learn many arbitrary functions, as opposed to just doing exactly what we need. But we think there's a middle ground between having custom predictors and a CNN. We think that we can have specialized components that help the CNN to achieve cost efficiency. So let's dig deeper into the inefficiencies of the CNN to understand it better. So to predict our case study branch, recall that we had to do 2 tasks. The first task was identifying the insertion branches in the global branch history. The convolution layer is actually very good at doing that. It can isolate each individual branch using the program counter. There is some inefficiency, but it's not a major problem. The more problematic part of the prediction is isolating the current recursive instance of qsort. In theory, the fully connected layer is responsible for doing that. But since this task is nonlinear, a single neuron is incapable of doing that. Even if we had multiple fully connected layers, we would need way too many neurons to be able to do this task. So for our purposes, I would say that it's impossible to do this task with a CNN. So how does the CNN achieve that high accuracy of more than 99%? It does that by detecting less reliable signals that it can see. Now, this is a fundamentally non-optimal way of branch prediction because because we're using more signals than necessary for predicting the branch. It achieves high accuracy in this case, but in turn, it inflates the size of the CNN model. To overcome this, we need to introduce components that help the CNN with the second task that it cannot do. And one of our proposals for doing that is to use input preprocessing. For example, if we can use static analysis to realize the recursive nature of the function, we can realize that we should only feed the current instance of qsort to the CNN. We could do that offline and build a component that can do that at runtime. Then the CNN can predict this branch with almost 100% accuracy with only 1 convolution filter and only 0.2 kilobytes of storage. Now, there are some details with our experiments that I glossed over, but I encourage you to read our paper to understand more. We've also covered many other research directions and that address challenges in training CNNs for branch prediction. Again, I encourage you to go and read our paper to understand more. In conclusion, what we did today was to go over a case study and use that to make observations about the sources of inefficiencies in CNNs. Then we made a case for specialization. We think that specialization is necessary for accurate and cost-efficient multi-layer neural network branch predictors. If you have any questions or feedback, please let us know. Thank you for watching.